Section: Introduction. In this section, we discuss how we are leveraging Retrieval-Augmented Generation (RAG) to enhance the trustworthiness of our commercial application that converts natural language into workflows. By using RAG, we aim to reduce hallucination, which is the generation of incorrect properties like non-existent steps or tables. Our workflows are represented as JSON documents, where each step is a JSON object. To illustrate, we provide an example of a text requirement and its corresponding JSON document in the figure. When it comes to enterprise users customizing their applications by adding their own workflow steps, it is crucial to minimize mismatches that may occur when the natural language input is not within the model's training data. While fine-tuning a large language model can lead to good workflows, there is a risk of hallucination, especially with out-of-distribution inputs. To address this, we employ RAG to reduce hallucination and improve the overall output quality. Our key contributions include demonstrating the application of RAG in workflow generation, showcasing how RAG mitigates hallucination, and highlighting that deploying a smaller LLM with a minimal retriever model can maintain performance without sacrificing accuracy. In the realm of retrieval-augmented generation, the typical approach involves retrieving relevant information before generating text to avoid inaccuracies. However, our work differs as we apply this technique to a structured output task, where we retrieve JSON objects to enhance the generated JSON document's validity and executability. The retriever plays a crucial role in this process, aligning semantics between natural language queries and structured JSON objects. Structured output tasks, such as text-to-code or text-to-SQL conversion, are challenging as they require generating interpretable and executable output. With the rise of large language models, tasks like these have become more accessible, enabling developers to write code efficiently. While code LLMs excel in various programming tasks, fine-tuning them for domain-specific schemas like JSON workflows requires additional steps to ensure accuracy and reduce hallucination. Another technique to combat hallucination in LLMs is guided generation using tools like outlines, which can help generate steps that exist within a given context. However, for tasks like workflow generation with customizable steps, relying solely on context-free grammar may not provide sufficient guidance on which steps to include based on the natural language query. Section Summary. In this section, we introduce the application of Retrieval-Augmented Generation, RAG, in workflow generation, aiming to reduce hallucination and enhance output quality. By leveraging RAG, we demonstrate the effectiveness of deploying a smaller LLM alongside a small retriever model without compromising performance. Our work focuses on structured output tasks, where JSON objects are retrieved to aid in generating executable workflows, differing from traditional RAG applications that retrieve facts for text generation tasks. Section: Methodology. In this section, we present the methodology we used for our RAG system. We illustrate the high-level architecture in a figure. To begin, we create indices of steps and tables during initialization using the retriever. When a user makes a request, the retriever suggests steps and tables, which are added to the user query to form the LLM prompt. The LLM then generates the workflow in JSON format through greedy decoding. To develop our system, we first train a retriever encoder to align natural language with JSON objects. Subsequently, we train an LLM in a RAG manner by incorporating the retriever's output in its prompt. For retriever training, we aim for the LLM to learn how to construct JSON documents that capture the relationship between workflow steps. The risk of hallucination mainly arises from step names, as there are numerous possible steps, and customers can also add their own steps. Additionally, some trigger steps require database table names, which can also be hallucinated. Hence, we train the retriever to map natural language to existing step and database table names. We fine-tune the retriever model to enhance the alignment between text and JSON objects and to create a better representation of our application domain. Unlike existing open-source sentence encoders, our setting involves unstructured queries or workflow requirements and structured JSON objects. Fine-tuning significantly improves retrieval results and allows the retriever to grasp the nuances specific to our domain. We utilize a Siamese transformer encoder with mean pooling to encode user queries, steps, and tables into fixed-length vectors. These vectors undergo normalization to have a norm of 1. The retriever is trained on pairs of user queries and corresponding steps or tables, including both positive and negative training pairs. During initialization, we establish an index of steps and tables using FAISS. When a user submits a natural language query, we embed the query using our retriever and retrieve the top K steps and tables based on cosine similarity. For LLM training, we choose to train the retriever and LLM separately for simplicity. We augment our dataset with suggested step and table names from the retriever and then proceed with standard LLM supervised fine-tuning. By incorporating the retriever's output in JSON format into the LLM input, we simplify the structured output task for the LLM. In each LLM training example, we assume the retriever has 100% recall, except for the most frequent steps. We present the LLM with numerous examples during training, using a concise format to reduce input tokens and clarify the structured output task. This approach has shown good performance, as discussed in a previous section. Section Summary. In this section, we present the methodology behind our RAG system. We initialize the system by creating indices of steps and tables using a retriever, which suggests steps and tables when a user makes a request. The retriever is trained to map natural language to JSON objects, and we fine-tune it to improve text to JSON mapping and enhance domain representation for better workflow generation. Section: Experiments. In this section, we were focused on experiments related to our task within a commercial enterprise system. We had to create our own datasets and evaluation metrics for this purpose. For our datasets, we gathered about 4,000 examples of workflows from our enterprise platform and had annotators write natural language requirements for them. Additionally, we generated around 1,000 samples with simple steps to help the model learn how to handle workflows that users build step by step. To ensure unbiased results when the system is in use, we had expert users interact with a simple interface to input their requirements, which we used to create another dataset called Human Eval. Our evaluation metrics are based on this Human Eval dataset rather than the test dataset because it provides higher quality and more realistic input. Some samples do not need triggers, and a few require the model to generate tables. However, a limitation of our data labeling is that our internal datasets mainly focus on IT, while our system can be used in various domains like HR and finance. To address this, we had annotators label 5 additional splits from different deployments to assess the system's performance in diverse settings. We trained a retriever encoder using examples from our datasets and evaluated its quality on the Human Eval split. The metrics we use to evaluate the entire system include Trigger Exact Match, M, Bag of Steps, BOFS, Hallucinated Tables, HT, and Hallucinated Steps, HS. We also used recall at 15 for steps and recall at 10 for tables to evaluate the retriever's performance. In terms of models, we had to balance model size and performance for both the LLM and the retriever encoder in our production system. We fine-tuned models of different sizes to see how it affects the final metrics. We compared our fine-tuned model with various sizes of off-the-shelf GTRT5 models to understand the impact of larger encoders on performance. The results of the retriever encoder showed that scaling the size of off-the-shelf encoders did not lead to significant improvements in retrieval metrics. Fine-tuning the encoder was crucial for enhancing performance, as observed in code retrieval tasks. After fine-tuning with all negative sampling strategies, the all-MP NetBase v2 model with 110M parameters performed the best. Section Summary. In this section, we devised our own datasets and evaluation metrics for our commercial enterprise system task. We extracted internal workflow examples and created datasets for natural language requirements, including a human eval split for unbiased quality estimation. We evaluated our RAG system using trigger exact match, bag of steps, hallucinated tables, and hallucinated steps metrics, and fine-tuned different sizes of LLMs and retriever encoders to measure their impact on system performance. Section: Retrieval-Augmented Generation. In this section, we aim to simplify and explain the concept of retrieval-augmented generation. We focus on reducing errors while maintaining high performance within our infrastructure limits. When we fine-tune our models without a retriever, we can see a high percentage of errors in the generated steps and tables. However, by using a retriever, these errors decrease significantly. All our models generate correct JSON documents as expected after fine-tuning. Scaling up the size of our models helps improve certain metrics, especially with Retrieval-Augmented Generation, RAG. Larger models can better incorporate retrieved information during generation. We find that larger models tend to perform better and hallucinate less compared to smaller models. We also compare our RAG fine-tuned 7B model with other models of the same size, such as Code Llama 7B and Mistral 7B v0.1. Surprisingly, despite fine-tuning with RAG, these models perform worse across all metrics compared to our StarCoder base 7B model. This suggests that pre-training on a large amount of natural language data may not be beneficial for our task. Next, we evaluate our approach's performance on out-of-domain (OOD) scenarios without further fine-tuning. Our results show that our model performs similarly on OOD data as on in-domain data, thanks to the retriever. When we remove suggestions during evaluation, the model's performance drops significantly, indicating the importance of suggestions in generating accurate workflows. We also analyze errors in the generated workflows, which can stem from issues in both the retriever and the language model. To improve the retriever's performance, we can break down queries into shorter texts for more precise retrieval. For errors in the language model, especially with logic-based steps like if or try, synthetic data generation can help address these issues. Our findings have influenced decisions regarding system scalability and modularity. Using a 7B parameter model has shown the best performance, allowing for larger batch sizes and increased system throughput. We can deploy a small encoder for the retriever on the same GPU without affecting the larger language model significantly. Decoupling the retriever and the language model enables easier reuse and independent optimization. We have ideas to further reduce system response time, such as changing the output format and streaming generated workflows back to the user step by step.